Hi, my name is Scott Kurtz, president of DSP Soundware. The purpose of this presentation is to present the sampling theorem using a more intuitive approach. If you're looking for formulas, you won't find them here in this presentation. But if you're looking to understand the sampling theorem in a way that was different than the way you were originally taught, you've come to the right place. We'll start with a brief review of digital sampling of analog signals. Here we have a woman, and she's presumably speaking, and her speech is carried through the air as varying air pressure. And you can see here's a plot of varying air pressure. The pressure increases, the pressure decreases. Obviously, this is slowed down a lot, and there would be a lot of increases and decreases based upon the content of her signal. Her signal is going from air pressure into the microphone and coming out as an electrical signal. So now we have a time-varying voltage, which looks the same as the time-varying air pressure. It's a representation of the time-varying air pressure using electrical voltage rather than air pressure. To get into the digital world, we use an analog to digital converter, which takes that electrical signal and converts it into a sequence of numbers that represent the original signal, but they're taken at equally spaced intervals. Then perhaps we have a digital to analog converter to go the other way. Typically, we would have something happening in between the analog digital and digital analog converters, some kind of processing or filtering or something along those lines. But for simplicity, we're taking those digital samples and feeding them right to a digital to analog converter in this diagram, which in turn turns those digital samples back into a time-varying voltage. And then we might send that signal to a speaker, which turns it right back to the original air pressure, which somebody could hear. So let's get to the sampling theorem. What the sampling theorem says basically is if a signal is band limited to B hertz, it can be sampled at greater than 2 times B hertz with no loss of information. This defies intuition, at least it did for me when I was taught it. What happens to the signal in between the samples? Don't we lose that information? So we see in this diagram we have an analog signal, sinusoid, and we have these little dots that are samples of that signal. And according to the sampling theorem, all we need to represent that entire signal is those individual dots or individual samples. And the thing that's not intuitive is what happens to all those samples or all those voltage levels or air pressure representations in between the samples? How can that not be a loss of information? So we're going to try to address that in an intuitive way, and hopefully we'll come away with a better understanding of why this is true, why the sampling theorem is true. So the rest of the demonstration is going to be in the form of a multimedia demo, but I wanted to describe what that demonstration is going to be before we get to it. We're going to see a Windows program. There's going to be a rotating phasor, and by selecting the imaginary component of that, we can come away with a sine wave, and we'll show the sine wave on a display in analog and digital form after a sampler. And then we'll also have a filter, a fast Fourier transform to convert to the frequency domain, and then a frequency domain display of it. And in fact, we'll have a second signal chain for comparison to the first. It'll make more sense once we get to it. So hold on to your hats, here we go. Okay, here's our demo program, and we'll take it through its paces just to show what it does, and then we'll apply it to the sampling theorem. So what we have here, we have we can specify signal frequency and sampling frequency for both sets of plots. We'll be able to see the phasor that's generating a sine wave in both cases, and then the frequency domain representation will really be just for the first time domain plot, or the first signal, not the second one. And we'll be able to show various things, and we can actually listen to the signal while we're playing it. So let's start out. We'll put out 1,000 hertz sine wave, and we can see what we expect as a regular old sine wave. And we see the samples occurring at a periodic rate. In this case, it's 8 kilohertz, but the demonstration is much slowed down so that it's easy to see. And I'll turn on the phaser also. So you can see that the red dots and the red signal are the analog signals, and the green dots, or the green phaser that jumps at a periodic rate, that's the sampled version. And if you look closely, you'll see, as expected, that the sine wave is the vertical component or the imaginary component of the phaser. And I'll single step that to make it easier to see. Okay, and let's see if this messes us up. We'll turn on the audio output and so you can hear what's going on as well. I think that's a little bit loud. Okay, and you can see that as we increase the frequency, you can hear the pitch go up. You can see the phasers moving faster, and you can see the sine wave periodicity increase. I'm going to turn that down so it's not too annoying, but I want to leave it on because it's nice to hear. And then we can turn on the frequency domain plot, and that's showing the frequency on a scale from 0 to 24 kilohertz. So we can watch as we lower the frequency, that changes. And the frequency domain plot has a 4 kilohertz low-pass filter being applied to it. So if we go above, or if we approach 4 kilohertz, then the signal gets filtered out. So getting back to the sampling theorem, I'm going to take a sort of a reverse approach to this and say, all right, we have a sampling frequency of 8,000 hertz or 8 kilohertz, and the maximum bandwidth that can represent without losing information is half of 8 kilohertz or 4 kilohertz. So what happens if we take our signal and make it go beyond 4 kilohertz? Let's see what the effect is. Let me turn off the frequency domain for the audio play out for a second, because that's going to be confusing at first. So we're 500 hertz above the maximum, which is 4 kilohertz. Let's go a little further to make the point a little better. What we see, or what we think we see, is the sampled phaser is going backwards instead of the original forward direction. And what's really happening is that the analog signal, the phase, is increasing by more than half of the circle in between samples. So it appears to be going, the sampled signal appears to be going backwards. So let's slow this down to see what's really happening. I'm going to do a single step. And you can see that the analog signal is going 3/4 of the way around the circle in between digital samples, and that's why it looks like the digital phaser is going backwards. So I want to show a comparison. I'm going to take this up to 7 kilohertz for the purpose of doing this demonstration. I'm going to turn on this second phaser, which I'll show both of the plots. So 7 kilohertz versus 1 kilohertz, both sampled at an 8 kilohertz sampling rate. Let's see what happens. Let me start that from scratch. Hold on a second. Nope, that didn't do it. Okay, so the top signal went around almost a full circle and sampled, whereas the bottom one went a fraction of the circle and sampled, and they're opposite of each other. They're negative of each other, give or take. There's some margin of error in this demonstration. So let me turn off the analog signal, and we'll show this again. Be more clear. So what we're seeing is that at a sampling rate of 8 kilohertz, A 1 kilohertz signal and a 7 kilohertz signal are the same, except that they're opposite in polarity. So they actually look like the same frequency. They have this, the same rate of number of cycles per second. That's telling us that there's some kind of ambiguity going on. And what we're doing is we're confirming that if you sample a signal whose frequency is greater than half the sampling rate, you don't really know what you've got. Is this a 7 kilohertz signal or is it a 1 kilohertz signal? And in fact, I would argue that it's both. And I'm going to show that by turning off the filter, turning on the frequency domain, and we'll see what happens. We'll turn on the audio playout also. If you have a good ear, you'll hear that that's no longer a pure signal. So what we have here, just a second, let me turn off the second one because it's confusing. We have a 7 kilohertz signal being sampled at 8 kilohertz, and I'll show the analog signal also. And in the frequency domain, it appears as if it's 1 kilohertz, 7 kilohertz, 9 kilohertz, and so on. And what we know from our DSP courses, that's aliasing. We can't really tell the difference except in phase between 1 kilohertz and 7 kilohertz. And in fact, if we look at 1 kilohertz and 9 kilohertz, they look identical, even in phase. And let's do that. Both plots. Set this one to 9 kilohertz and resume. And I'll turn off the analog signal and it'll be even clearer. So that's a justification for the sampling theorem, in that if you try to sample a signal whose bandwidth is greater than half the sampling rate, you really don't know what you have. In other words, you've lost information. So I think what we've done here is shown a reverse proof almost, or rather than state that you must sample at least or greater than twice the bandwidth of a signal, we've shown what happens if you don't do that, and clearly you lose information and you introduce ambiguity into what you've sampled. You don't really know what you have. A 1 kilohertz signal in appearance could look like 7 or 9, etc. I just want to make one more point, even though it's sort of outside the scope of this demonstration or presentation, but we tend to think about the sampling theorem in terms of a low-pass signal, but in fact we can use it for bandpass signals as well. For example, if we want to sample a signal that is in the range of 4 to 8 kilohertz, let's try that out here. We'll start out with a signal frequency of 1500 hertz. It shows up in the 4 to 8 kilohertz band because of aliasing. But what happens if we go into the 4 to 8 kilohertz band? Now we have a correct representation. We have 4500 hertz in. We're showing 4500 hertz. And we go to 6000 hertz. Again, we're still in showing 6000 hertz. So anything in this band is being represented correctly. The point that I'm trying to make is that if we know that a signal is band limited, for example, to between 4 and 8 kilohertz, we can still sample it at 8 kilohertz because the bandwidth is less than 4 kilohertz. So even the 6 kilohertz signal that we had coming out, the frequency is greater than half the sampling rate, but the bandwidth is still less than 4 kilohertz. Therefore, we can sample it at 8 kilohertz with no loss of information. So, in summary, hopefully this demonstration has given you a new way to look at the sampling theorem. If you found the presentation useful, please let your friends and colleagues know about it. And for more information about my company, DSP Soundware, visit our website at www.dspsoundware.com. Thank you very much for listening, and have a good day.